Good afternoon, everyone. I am Lauren Tan, your first speaker for group number 7. And today we will be discussing about the angular modulation. Angular modulation is a modulation technique wherein the amplitude of the carrier is kept constant while the angle or the argument of the carrier is varied in accordance with the intelligent signal. The term modulation here simply means the exertion of controlling influence onto something. There are two kinds of angular modulation, the frequency modulation and phase modulation. To distinguish one from another, we have an example equation of a wave here. The wave signal equation consists of A, the amplitude, and this whole term here, the angle. The angle consists of this term, which is 2 pi ft, where f stands for frequency. If we will be varying this part and kept this t and a constant, that will be called as frequency modulation. And if we will be keeping this t, which is the phase angle constant, and remain this whole part of the equation constant, this will be called as phase modulation. And from the previous group, they kept this A amplitude varying while this whole thing constant, and they explained what amplitude modulation is. Now for the next slide, we have the figure here where modulation is shown. There will be two inputs, the modulating signal and the carrier signal. Then this box will be varying depending on what will be the modulator used. If it is a phase modulator, it is used in data communications. But if it is frequency modulator, it will be used in radio broadcasting and direct satellite broadcasting. This modulated signal here have benefits. So why do we do this modulator thing? Now, first, we have to separate signal from different transmitters. For instance, we have audio frequencies that are within the range of 20 Hz to 20 kHz. Without modulation, all signals at same frequencies from different transmitters would be mixed up, thereby giving impossible situation to tune to any one of them. In order to separate the various signals, radio stations must broadcast at different frequencies. Each radio station must give its own frequency band. This is achieved by frequency translation as a result of modulation process. Now, the second reason why we modulate the signal is to reduce the size of the antenna. For efficient transmission, the transmitting antennas should have length at least equal to a quarter of the wavelength of the signal to be transmitted. For an electromagnetic wave of frequency 15 kHz, the wavelength is 20 km and 1/4 of this will be equal to 5 km. Obviously, a vertical antenna of this size is impracticable. On the other hand, for a frequency of 1 MHz, this height is reduced to 75 meters. Also, the power radiated by an antenna of length is proportional to the lambda. This shows that for the same antenna length, the power radiated is large for shorter wavelength. Thus, our signal, which is of low frequency, must be translated to the high frequency spectrum of the electromagnetic wave. This is achieved by the process of modulation. Then, we have to transmit the information to long distance without interference. without modulation, we can not achieve this. Then we can use this to reduce the bandwidth. Then for frequency modulation, it is a form of angle modulation where the frequency of the carrier is varied in accordance with the instantaneous value of the intelligence. Here, as I've said earlier, we will be varying this f frequency and keeping this theta and a constant. Now, for the equation of frequency modulation, it is expressed mathematically as E sub Fm equal to E sub c sine theta, where this theta here is equal to the omega t plus m sub f times the sine of omega sub m times t, where this EFM is equal to the instantaneous value of the M signal, which is in volts, and the 2 omega is the angular velocity of the carrier, which stands for this C, and of the intelligence, which is for M, or the modulating signal, which is in rad per second. Then the M sub F is the modulation index. This F here express the meaning of frequency because modulation index is different from one another. Then we have this E sub C, which is the peak amplitude of the carrier, which is also in volts.
Good afternoon. I am Singmin Sijan and I will be the second speaker of group number 7. The first topic that I will discuss is all about frequency deviation. Frequency deviation is the amount of change in the carrier frequency produced by the modulating signal. Frequency deviation is used in FM radio to describe the maximum difference between an FM modulated frequency and the nominal carrier frequency. The term is sometimes mistakenly used as synonymous with frequency drift, which is an unintended offset of an oscillator from its nominal frequency. The equation of frequency deviation states that delta is directly proportional to the peak intelligence amplitude. As you can see here, this is the frequency deviation equation, where delta is the frequency deviation, K is the deviation sensitivity, and E sub m is the peak intelligence signal amplitude. Now let's have an example. What is the frequency deviation of an FM transmitter whose deviation sensitivity is 25 kHz per volt and its peak intelligence signal amplitude is 10 volts? The given in this example is that the deviation sensitivity is 25 kHz per volts and the peak intelligence signal amplitude is 10 volts. Plugging in the given into the equation gives us a product of 250 kHz. Now, let's proceed to the next topic. Modulation index. Modulation index is the ratio of the frequency deviation over modulating frequency. The modulation index or modulation depth of an modulation scheme describes about how much the modulated variable of the carrier signal varies around its unmodulated level. It is defined differently in each modulation scheme. As you can see, this is the equation of the modulation index, where delta is the maximum frequency shift caused by the intelligence signal, f sub m as intelligence frequency, and m sub f is the modulation index. Now let's have an example. What is the modulation index of an FM transmitter whose frequency deviation is 60 kHz and its audio frequency is 20 kHz? Now, the given of this example is that the frequency deviation or delta is 60 kHz and the audio frequency is 20 kHz. Plugging in the given in the equations give equations. And now, let's have an example. What is the modulation index of an FM transmitter whose frequency deviation is 60 kHz and its audio frequency is 20 kHz? The given in this example is that the frequency deviation or delta is 60 kHz and the audio frequency or the F sub m is 20 kHz. Plugging the given into the equation gives us a quotient of 30 kHz. And now, let's proceed to the last topic that I will discuss. The last topic that I will discuss is all about the FM percent modulation. In here, we will see the equation of the FM percent modulation, where the delta max is the maximum carrier deviation, delta actual is the actual carrier deviation, and the percent m sub f is the FM percent modulation. Now, let's have an example. What is the FM percent modulation of an FM transmitter whose actual carrier deviation is 75 kHz and its maximum carrier deviation is 10 kHz? The given in this example is that the delta actual is 75 kHz and the delta max is 10 kHz. Plugging in the equation gives us a percentage of 7.5. So this is my last topic. Thank you.
Good afternoon, everyone. My name is Amar David Gizan, and I'm gonna report about deviation ratio. Deviation ratio is used whenever the maximum allowable frequency deviation and the maximum modulating frequency are used in computing the modulation index. Another is expression of the worst case modulation index. The formula in the deviation ratio is stated in here, where this sign is the maximum carrier deviation and this sign is the maximum allowable intelligence frequency in hertz. DR is also stated as deviation ratio. In deviation ratio, there are FC zeros, where they are arranged in the maximum carrier deviation and in the maximum allowable intelligence frequency. In FM, the maximum carrier deviation is in 75 kHz, while the maximum allowable intelligence frequency is in 15 kHz. In TV sound, the maximum carrier deviation is in 25 kHz, and the maximum allowable intelligence frequency is in 15 kHz. In public safety services, the maximum carrier deviation is in 5 kHz, and the maximum allowable intelligence frequency is in 3 kHz. Lastly, the amateur band ratio, the maximum carrier deviation is in 3 kHz, while the maximum allowable intelligence frequency is in 3 kHz also. EFM can be written using the Bessel function. This is the Bessel function, and adding the J, which is this amplitude of the side frequency, and see that it depends on each amplitude of the side frequency, where J sub 0 is the carrier component, J1 is the first set if side frequency is displaced from the carrier by FM, J2 set is the second set if side frequency is displaced from the carrier by 2 FM, J sub 3 is the third set if side frequency is displayed from the carrier by 3 FM. So, we can see here that J sub 0 is this sign, while J sub 1 is this sign. It adds up every set of the frequency until the limit of the amplitude of the side frequencies. The amplitude of the side frequencies J sub n is given by the equation. So in computing the EFM, we must first find J sub n, plugging the formula, this one, in this part, so we can find the EFM in each J. An example of a deviation ratio is, what is the deviation ratio of an FM signal of the maximum allowable deviation is 12 kHz, and the maximum intelligent frequency is 4 kHz. Using the deviation ratio formula, which is the maximum carrier deviation over the maximum allowable intelligent frequency, we can say that the deviation ratio is 12 kHz all over 4 kHz. Deviation ratio is equal to 3 kHz. In here, we can see the Bessel function table, where you can see where we can compute J, the carrier, using the modulation index. We can see that J sub 0 is the carrier component, while J1, J2, J3, and so on is the side frequency pairs. It depends on the modulation index in the carrier component. Moving on to the next topic, which is the bandwidth of FM. There are 4 types of computing the bandwidth of FM. First is practical bandwidth using Bessel functions, where bandwidth is equal to F sub use USB minus F sub LSB is equal to F sub C plus N times F sub M minus F sub C minus N times F sub M, where the bandwidth is equal to 2 times F sub M times the number of sidebands. In the Carson's formula, bandwidth is equal to 2 times F sub M plus this sign is equal to 2 times 1 plus M sub F times F sub M. While the narrow band, BW or bandwidth is equal to 2 times FM. For an FM signal where the M sub F is less than pi over 2. Another thing for the Carson's formula, there are certain conditions in computing the Carson's formula. First is the number of sidebands selected should be the minimum number that will result in the transmission of no less than 98% of the total power. And the significant sidebands considered are greater than 2% of the carrier. This is the condition for the Carson's formula. Moving on to the wideband, where bandwidth is equal to 2 times sigma for an FM signal where M sub F is greater than pi over 2. So this is my topic, bandwidth of FM and the deviation ratio. Thank you for listening. Moving on to the next reporter.
Good afternoon. I'm Sofia Raziel Cidi Guzman, and I will be your fourth speaker. First, I will enumerate to you the observations on FM. FM has a carrier and an infinite number of sidebands. These sidebands are separated from the carrier by FM, 2FM, 3FM, and so on, resulting to have recurrence frequency of FM, or also known as intelligence frequency. The J coefficients eventually decrease in value as n increases. Third, the modulation index determines how many sideband components have significant amplitudes. The sidebands at equal distance from FC have equal amplitudes. The J coefficients occasionally have negative values, signifying a 180 out-of-phase change for that particular pair of sidebands. As MF increases, so does the value of a particular J coefficient. MF is inversely proportional to the modulating frequency, and the amplitude of distant sidebands increases when the modulation frequency is lowered. The total transmitted power always remains constant, but with an increased depth of modulation. This will result, so the required here is the bandwidth is increased. The next slide is a continuation on the enumerating observations of FM. The theoretical bandwidth required in FM is infinite. In practice, the bandwidth used is one that has been calculated to allow all significant amplitudes of sidebands components under the most exacting conditions. In FM, the amplitude of the carrier component does not remain constant. Its J coefficient is J sub 0, which is a function of FMF. Last, it is possible for the carrier component of the FM wave to disappear completely. This happens in certain values of the modulation index called eigenvalues. So the graph shows that these are approximately 2.4, 5.5, 8.6, 11.8, and so on. This disappearance form a handy basis for measuring deviation. In the next slide is the advantages of FM over AM. FM has better noise immunity and also rejection of interfering signals because of capturing effect. Another is better transmitter efficiency. Aside from advantages, we also have disadvantages of FM over AM. FM has a large bandwidth, more complex and expensive circuits, and a limited reception. So in this next part, shows to you a FM varactor modulator. This is a frequency modulator circuit that uses varactor diode to change the oscillator in accordance with the modulating voltage. So in this figure, shows the basic concept of a varactor frequency modulator. The L1 and C1 here in this part represent the tuned circuit of the carrier oscillator. Our diode is this one in the diagram is connected in series with a capacitor across the tuned circuit. The value of the second capacitor in this part is made very large at the operating frequency so that its reactance is very low. As a result, when capacitor 2, or again this part, is connected in series with the lower capacitance of D1 or the varactor diode, the effect is as if the varactor diode were connected directly across the tuned circuit. So the total effective circuit capacitance then is the capacitance of the varactor diode in parallel with the first capacitance. This fixes the center carrier frequency. The capacitance of the varactor diode is controlled by two factors: a fixed DC bias and the modulating signal. So in the figure, the bias on the D1 or the varactor diode is set by the voltage divider, which is made up of R1 and R2. This part. The modulating signal is applied through the capacitor 3 and the RFC. The C3 is a blocking capacitor that keeps the DC bias out of the modulating signal circuits. So as this goes on, the modulating signal varies. It adds to or subtracts from the fixed bias voltage. Thus, The effective voltage applied to D1 or varactor diode causes its capacitance to vary. This in turn produces a deviation of the center frequency as desired. So the next part is the FM receiver circuit. So these are devices that are able to receive FM signals. We have few components needed for a receiving circuit. It uses first is antenna, RF amplifier, tuner, detector, and audio amplifier. The RF amplifier, this part, is a sensitive amplifier that amplifies the very weak radio frequency signal from the antenna. The antenna is in this part. Next is the tuner. It is a circuit that can extract signals of a particular frequency from a mix of signals of different frequencies. The detector is responsible for separating the audio information from the carrier wave. And last is the audio amplifier. This component is to amplify the weak signal that comes from the detector so that it can be heard. This can be done using a simple transistor amplifier circuit. So it is this last part. The next slide will be the pre-emphasis circuit. This kind of circuit boosts the high audio frequencies in modulation at the transmitter, and it is used to improve the signal-to-noise ratio. So at the transmitter, the modulating signal is passed through a simple network which amplifies the high frequency components more than the low frequency components. The simplest form of such a circuit is a simple high-pass filter of the type shown in this figure. Specifications dictate a time constant of 75 microseconds, where tau, the equation here, is equal to the product of the resistor 1 and the capacitance. Any combination of resistor and a capacitor giving this time constant will be satisfactory. Such circuit has a cutoff frequency of 2122 Hz. This means that frequencies higher than 2122 Hz will be linearly enhanced. So the other two equations here will be used to get the two frequencies. The last topic is that the emphasis circuit. This kind of circuit will attenuate the high audio frequencies in the receiver in the same amount that it is boosted to compensate for the effect of the pre-emphasis circuit. So, as a continuation, to return the frequency response to its normal level, at the emphasis circuit, this figure, is used at the receiver. So this is a simple low-pass filter with a constant of 75 microseconds. So this figure features a cutoff of 2122 Hz and causes signals above this frequency to be attenuated at the rate of 6 decibels per octave. So as a result, in using this circuit, the pre-emphasis of the transmitter is exactly offset by the de-emphasis circuit in the receiver, providing a normal frequency response. The combined effect of pre-emphasis and the de-emphasis is to increase the high-frequency components during transmission so that they will be stronger and not masked by noise. So this would be my last topic, and we will have the next speaker.
I'm Rowan Junel Bibilton, and I'm here to discuss about the phase modulation in comparison of FM and PM. Phase modulation is a modulation pattern for conditioning communication signals for transmission. It encodes a message signal as variations in the instantaneous phase of a carrier wave. Phase modulation is one of the two principal forms of angle modulation, together with frequency modulation. The phase of a carrier signal is modulated to follow the changing signal level of the message signal. The peak amplitude and the frequency of the carrier signal are maintained constant, but as the amplitude of the message signal changes, the phase of the carrier changes correspondingly. PM changes the phase angle of the complex envelope in direct proportion to the message signal. Suppose that the signal to be sent, called the modulating or message signal, and the carrier onto which the signal is to be modulated, is equal to the carrier amplitude times sine of carrier frequency times time plus phase shift. And this makes the modulated signal carrier amplitude times sine multiplied by carrier frequency times time plus the modulating signal plus the phase shift. Frequency modulation. In telecommunication and signal processing, frequency modulation is the encoding of information in a carrier wave by varying the instantaneous frequency of the wave. In analog frequency modulation, such as FM radio broadcasting of an audio signal representing voice or music, the instantaneous frequency deviation, the difference between the frequency of the carrier and its center frequency, is proportional to the modulating signal. FM receiver circuit. This is the most simple FM receiver with good performances that works great even if the sensitivity is not too high. The working principle of this radio receiver may seem a little unusual. It is made of an oscillator that is synchronized with the received frequency of T1, which works as a broadband preamplifier in VHF range. So how does the FM receiver works? Because of the synchronization, the oscillator output will have the same frequency deviation as the received signal from the FM antenna. These deviations are caused by the broadcasted audio information. FM varactor modulator. FM varactor is another FM modulator which is widely used in transistorized circuit that uses a voltage variable capacitor. The varactor is simply a diode or PN junction that is designed to have a certain amount of capacitance between junctions. The capacitance of a varactor, as with regular capacitor, is determined by the area of the capacitor plates and the distance between the plates. The depletion region in the varactor is the dielectric and is located between the P and the N elements, which serve as the plates. FM spectrum. For the case of a carrier modulated by a single sine wave, the resulting frequency spectrum can be calculated using the Bessel functions of the first kind. As a function of the sideband number and the modulation index, the carrier and the sideband amplitudes are illustrated for different modulation indices of FM signals. For particular values of the modulation index, the carrier amplitude becomes 0 and all the signal power is in the sidebands. Since the sidebands are on both sides of the carrier, their count is doubled and then multiplied by the modulating frequency to find the bandwidth.